Welcome to the course on nanostructured materials, synthesis, properties, self-assembly and applications. We are in the module 4 of this course, and we are working on photocatalysis right now, and we had 2 lectures on photocatalysis, and today is the third lecture on photocatalysis, and this is also the lecture 3 of module 4. So, in photocatalysis, in the previous lectures we looked at the basic ideas of catalysis in the presence of light, and how UV light and visible light catalyze reactions through the generation of electrons and holes. And 2 important criteria are: the electron and hole should be generated efficiently, and the second thing is the electron and hole should be separated from each other, so that they do not recombine and release a photon. So, this recombination has to be prevented, and this charge separation is an important part in the design of new materials, which will allow for enhanced efficiency of the photocatalyst. Now, the photocatalysis, as we see, you can have high surface area, small crystalline size. Especially we are discussing for titanium dioxide, and in this case the anatase form of titanium dioxide is very important. There are 3 forms of titanium dioxide. The rutile form is the high temperature form, whereas the anatase form is the low temperature form, and we require the anatase form for high photocatalytic activity. So, the anatase form is very important. Then TiO2 photocatalyst can be prepared with high crystallinity, it can be prepared with high porosity. So, porous structures of titania can be prevented, and the activation through a light source is possible in TiO2. Let us look at the conditions affecting the photocatalytic activity of TiO2. Now, TiO2 is normally prepared through an alkoxide. Through solution methods, we start from a titanium alkoxide, and typically we take titanium isopropoxide, and when you hydrolyze it with water, you get this kind of hydrates at low temperature, and then when you heat it further, you calcine it, you get the anatase form of TiO2. If you heat it further, that is, you further calcine, you get the rutile form of TiO2. Now, if you look at the properties, if you have at low temperature, you normally have the amorphous form, and at low temperatures you have very low surface area. In this case, you have a large, when you have large crystallinity, especially like in rutile. So, if you have the surface area which is low, and you may have very large surface area, both are possible, the activity goes down if the surface area goes down. So, the activity will be large when the surface area is very high, and the activity will become small when the surface area is small. In crystallinity, if you have very high crystallinity, then which you get at high temperatures, and in the rutile form you will get this high crystallinity. In the anatase form, somewhere in the middle, you have reasonable crystallinity and reasonable surface area, whereas in the rutile form you have high crystallinity and small surface area. And the difference between rutile and anatase in their band gap, anatase has a band gap of 3.2 electron volts, and rutile has a band gap of 3 electron volts. So, if you decrease the surface area, the number of active sites also decrease. So, what you want is a very a balance between crystallinity and surface area, and that you achieve in the middle, because if you have very amorphous type of TiO2 which you will get in the initial stages of the hydrate formation, then your active sites will be low, although you are having a high surface area because of poor crystallinity. So, it is good to work in this region where you have the anatase form of TiO2. Now, TiO2 is a very efficient photocatalyst, but you need ultraviolet radiation, UV light. Normally, we would like to use visible light, and to use the solar spectrum we would like to use the visible light, and the material should be active under visible light. Visible light is in the lower energy region compared to UV light. So, visible light active photocatalyst is really needed for practical applications and will be economical if we have efficient visible light catalyst. So, how do we modify the normal TiO2 which is a UV light photocatalyst to make it into a visible light photocatalyst, and that can be done by doping TiO2 with different materials like non-metals, transition metals or organic dyes. All of them can modify the behavior of TiO2 with respect to the incoming radiation, and all of them you have to choose appropriately the type of non-metal or transition metal or organic dye to control the band gap of TiO2 or effectively generate electron and hole pairs by using visible light instead of ultraviolet light. You can also increase the activity of the catalyst by loading a metal oxide, and we will see examples of these. The metal oxide typically reduces the chance of recombination of the electrons and holes which are produced during the photocatalytic reactions. So, hence there are several ways by which people are trying to use dopants to modify the band gap or to effectively create electrons and holes in the using visible light, because TiO2 is available in large amounts in the earth, and TiO2 is environmental friendly. So, it is a very challenging problem and important problem to convert TiO2 to a visible light photocatalyst instead of a UV photocatalyst. Now, how do you make titanium dioxide if you have to make it in the lab? Titanium dioxide is of course available in nature also, but you want to make titanium dioxide in the lab or in industry in bulk quantities. So, how do you make titanium dioxide which is active, and hence you want to make anatase form of titanium dioxide. So, people have found several methods like the hydrolysis of chlorides or sulfates of titanium salts, and they have used the sol gel method, which is a very popular method and we have discussed in our earlier lectures, or they have used the hydrothermal method where you use Teflon or steel containers to create a pressure in either aqueous medium or using a solvent, and some pressure is created and reaction occurs under pressure at temperatures around 100 to 200 250 degrees centigrade, or maybe sometimes up to 300 350 degrees centigrade. And there is another method which is the micro emulsion method, where you use titanium salts and appropriate surfactants to make micro emulsions, where you can make nano reactors using these micro emulsions which are present in solution. Depending on the type of surfactant and solvent, you can control the size of the nano reactors, and then you can do reactions using the titanium salts and hydrolyze them within the nano reactors to give you nanoparticles of TiO2 which are of the anatase form after certain calcination step. So, people can have used all these methods to make titanium oxide nano powders in large amounts and in the anatase form. Now, this is another technique by which TiO2 can be synthesized. This is the metal organic chemical vapor deposition, or MOCVD in general as it is told, where you have your material which can be titanium isopropoxide as discussed earlier. So, it is an alkoxide of titanium, and that passes through a heater, and there are several other heaters and temperature sensors in the furnace. So, there is a furnace through which this titanium isopropoxide is passed in the presence of oxygen and argon, and then at this temperature which you can control, the titanium isopropoxide can be calcined over a substrate, and TiO2 is generated on top of a substrate. And if you want some metals to be doped or metal oxides to be doped, then you put this metal oxide or metal as a dopant here, and the temperature should be sufficient to volatilize this dopant, and then the dopant mixes with the incoming stream of the titanium isopropoxide and forms TiO2 on this substrate along with the metal or metal oxide dopant. And this kind of system can generate large amount of very high quality films of TiO2 on the surface of appropriately chosen substrates. Substrates can vary from silicon to glass to quartz, and a variety of substrates you can choose depending on what is your application of this photocatalyst. Now, so how do we modify TiO2? Because we just discussed that we want to modify TiO2, which is a visible light UV light catalyst in general, but we want to use visible light. So, how do we modify this TiO2? By doping metals, metal oxides, and what happens when you dope metal and metal oxides to the band gap or to the valence band levels or to the conduction band levels. So, this is a kind of a graphic to show you that when the photons fall on the photocatalyst, which has got some metal particles on top. So, it is a metal doped TiO2. So, we have modified TiO2 with a metal, the metal particles are here, and this is the titanium dioxide particle, and when light falls on this particle TiO2, then electrons and holes are generated. Now, the electrons if they can migrate to the surface and meets the metal is an efficient conductor. So, this will take away this electron quickly, and so the electron, this electron which is produced here is separated from the hole, and that is what is one of the important points, how to separate electron and hole. And because of this metal dopant, the electron has this tendency to go to the metal, and the metal is a good conductor, and then it removes the electron. So, the electron and hole are separated. So, both the properties, generation of electron and hole pair and transport of electron and hole away from each other such that they do not recombine, both then can be met, which makes then this material, this metal doped TiO2 will be good for photocatalysis. Now, you can also dope a semiconductor. So, cadmium sulphide is a semiconductor, and this is your original TiO2 particle. So, assume that you have cadmium sulphide particle doped in TiO2. Now, TiO2 has a band gap of 3.2 electron volts, and this is the valence band and this is the conduction band level of TiO2, whereas cadmium sulphide has a smaller band gap of 2.5 electron volt. So, it can take lower energy and create electron hole pair. So, cadmium sulphide can be triggered to generate electrons and holes with lower energy of 2.5 electron volt, whereas TiO2 will require 3.2 electron volt. So, lower energy if you give, you can still generate electron and hole because of the presence of cadmium sulphide. Then this electron can migrate to the conduction band of the TiO2 and the hole this hole is generated in the cadmium sulphide. So, when the light falls on cadmium sulphide, the electron goes to the conduction band and the electron is transferred to the TiO2, and so the electron and hole are separated now on two different particles. The hole is retained on the cadmium sulphide and the electron goes to the TiO2. Now, this is this was metal doped TiO2, this was semiconductor doped TiO2, and then you can have an organic dye doped TiO2. So, if an organic dye is doped in TiO2, then what happens is this energy level of the energy gap of the organic dye to create an electron when light falls is, suppose it is in the visible, then this electron goes to the excited state of the dye is now in an excited state, and then the electron from the conduction levels or the higher orbital is transferred to the conduction band of TiO2, and then you can have some acceptor molecules which will take over this electron. So, from the conduction band of TiO2, the electron can be accepted by say an acceptor, and that acceptor will get reduced. So, A will get reduced to A minus because the electron will be transferred from the conduction band of TiO2 to the acceptor. So, three particular cases we looked at: modification of TiO2, metal doped modification of TiO2, semiconductor doped modification of TiO2, and then organic dye doped TiO2, which we call dye sensitized solar cells, is a very important area in which you are using a dye to start this mechanism of electron being generated and then electron hole being separated. So, if you look at the band diagrams, you can create different types of levels. So, suppose this is the original levels, this is the conduction band of TiO2 and this is the valence band of TiO2, and when you are doping transition metals, it is possible to have choose a transition metal such that you now have levels which are lower than the conduction band of TiO2. So, the electron will be here because it is lower in energy than this, and you can have a hole in the lower energy level, or you can have a non-metal doping TiO2, then you have a energy level which is higher than the valence band of TiO2. So, this is the valence band of TiO2, and so it is higher than the valence band of TiO2, and the electron this energy may be close to the conduction band of TiO2. So, either you can lower the conduction band or you can increase the energy of the valence band electron or hole, valence band hole. So, the hole will be here and the electron is here. So, these are two modifications to the bare TiO2 which is shown here. So, this is also possible and this is also possible. So, this kind of changes in the band diagram by doping is called generally band gap engineering, and you can also sensitize or increase the efficiency of titanium dioxide nanoparticles by using metal particles through their plasmon resonance. Now, we all know when you have metal nanoparticles, the conduction electrons of the metal nanoparticles can have collective oscillations. Now, these collective oscillations of the conduction electrons can sensitize the TiO2 nanoparticles, and this has been observed for silver, gold, copper nanoparticles, where they exhibit plasmon resonance in the visible range. So, you shine light in the visible and the conduction electrons of the metal nanoparticles like silver or gold then get excited, and you have these collective oscillations, and then this excitation acts like an antenna. The metal particle acts as an antenna because this collective oscillation is generated by trapping the visible light energy or the solar energy, and then it can enhance the catalysis of TiO2. Once the silver nanoparticle, which is doped on top of TiO2 acting as an antenna, catches the visible light radiation, and then it can create electrons and holes in the TiO2 to which it is connected. So, this is what is shown here. So, you have this metal particle and you have the TiO2. So, this is the conduction band of TiO2, this is the valence band of TiO2. Now, what can happen is if you use UV light, then you can excite this. So, you can create electron here and hole here in the TiO2, and when you create electrons here, then another property of the metal is that it can quickly take away the electron, and then it can reduce any species. For example, oxygen gas can be reduced to this kind of superoxide ion. Now, this reduction is possible because the electron generated in the conduction band of titania or TiO2 is quickly transferred to the metal, and the metal then the electron in the conduction band of the metal can get will reduce this oxygen, and the hole which is in the valence band can be used to oxidize some species. So, this is another possibility where you are using UV light, but the metal is enhancing the application of the electron and the hole, that is the reducing and the oxidizing capabilities are enhanced by the presence of the metal. In the previous case, these surface plasmons are basically acting as an antenna to trap energy in the visible spectral range, and then it helps in the sensitization of the titanium nanoparticles. In this case, you are not using the visible light, you are using UV light, but you are efficiently removing the electron and hole because of the conduction properties of the metal, and the metal then can quickly reduce some molecule which may be oxygen and give you this superoxide ion. Now, you can have so here the metal nanoparticles act as an electron sink, as I mentioned earlier, and it promotes interfacial charge transfer, and basically it reduces the probability that the electron created in the conduction band of TiO2 will interact with the hole on TiO2, because the electron is being removed from there. So, the metal is acting as a electron sink. Now, you can also have more complex nanostructures where you can have metal decorated on core shell nanoparticles. So, core shell nanoparticles, we know that there is one particle and it is covered by something else. So, the particle inside is the core and the material which is covered outside is the shell. So, here you can have metals like silver, gold, or alloys like silver, gold, or copper, nickel, or and you can make a large number of alloys of various sizes, say between 5 to 150 nanometers. Then you take this metal particle inside, and on the outside this gray part you put your titanium oxide, and there are methods by which you can make this shell out of pure titanium oxide. So, the smaller particles the better, you will have higher catalytic property, the efficiency will be high. So, if you have small particles of TiO2 and you make a shell around the metal nanoparticles, then you will get a structure of this. So, that will be core shell nanoparticle, but in this case it is metal decorated core shell. That means, on top of the TiO2 you again have either some metal or metal oxide. So, either metal or metal oxide, you can choose one of them, and depending on that you will have now plasmon enhanced separation of electron hole pair. So, this metal nanoparticle will be activated by the light, and you will have this plasmons, surface plasmons, because of the oscillations of the conduction electrons, and that will couple to the TiO2, and then you will get electron and holes. And if you have a particle like a metal like platinum, then the electron will quickly get separated onto the platinum, and then the hole will reside in the core and the electron will move to the surface. So, you have effectively separated the hole and the electron. If you use an oxide like ruthenium oxide, then it does not take up the electron like platinum does, but it will remove the hole. So, then the electron will remain in the core and the hole will go to the surface. So, depending on whether you have put platinum or you have put ruthenium dioxide on the surface of the TiO2, you can have the hole on the TiO2 on the RuO2 surface. So, hole will be removed from the metal, or if you put metal particles like platinum on the surface of the TiO2, then electrons can be removed more effectively, and then the hole will remain inside the core of the core shell nanoparticles. So, this is a very efficient and interesting design of core shell metal oxide nanostructures, where you have 3 materials designed. You have a inner core which is made of metal nanoparticle like silver, gold, platinum or something, and then you have a shell of titanium dioxide, and on top of that you have some decoration of small particles of either metal and metal or metal oxide, and these particles on the surface which decorate the surface of TiO2 act as a sink for either the electron or the hole. So, as we discussed, if it is platinum particles on the surface, it will act as a sink for electrons, and then the hole are inside the core and the electron is on the surface. So, they are charge separated. So, the efficiency of the photocatalysis is enhanced. The opposite is the hole goes to the surface and the electron stays in the core, and that is possible if you use ruthenium dioxide as particles decorating on the surface. Now, if you have metal particles covered with TiO2 covered with SiO2 or TiO2, then the visible light is not active, because TiO2 will not activate will not generate electron or holes, because the band gap of TiO2 is 3.2 electron volts, and the visible light is insufficient in energy to create electrons and holes. So, this is not possible. However, if you shine UV light and you have the metal and you have TiO2, then you can have electrons and holes, but the metal core shortens the electron hole pairs. So, they recombine, and hence you do not get charge separation easily, and so this is not going to be a very efficient photocatalyst. Although you will generate electron and hole, but the lifetime of the electron and hole will be very small and they will quickly recombine. So, this is also not a good situation. Now, the third situation is that you have a metal particle inside, then you put a layer of something like silica, this brown part, and then on top of that you put titania, and titania is a efficient UV photocatalyst, and this titania which creates the electron and holes, because of the silica coating, the electron which goes towards the metal will not be recombining with the hole. So, electron hole recombination will be prevented by the presence of an intermediate thin layer of silica. So, this is another design of core shell structures, where you have made titania to be active in the UV efficiently. Of course, still it is not active in the visible with this configuration, but it is active in the UV and the efficiency is high by putting a silica layer in between the metal core and the outside titania, which will actually create electron hole pair when UV light shines on it. So, these are three models. One model not effective in visible light, second model not effective in visible light and also not effective efficiently in UV light, and this is a model which is not effective in visible light, but very good catalyst in UV light. Now, if what is the role of the metal oxide? You can dope metals we studied have different role, and we looked at several cases of metal doping, how it can remove the electron if it is outside and what it does if it is in the core. Now, look at metal oxide and choose a metal which can have variable oxidation states. Now, these can lot of all transition metal oxides show variable oxidation states. For example, iron shows oxidation states of 2 plus, 3 plus, sometimes 4 plus, and in extreme cases even 6 plus. So, you can have iron at with various oxidation states. Similarly, you can also have cobalt with 2 plus, 3 plus, or vanadium 4 plus, 5 plus, etc. So, if you choose a metal oxide which can show variable oxidation states and dope it with a titania TiO2, then it can be a very good photocatalyst in the visible rate. So, how does that happen? You have again the large sphere showing you TiO2 particle and the band gap of TiO2. This is the conduction band and valence band, and now you have doped this titanium dioxide with metal oxide, and the metal oxide that you have chosen is iron oxide. So, iron oxide will have possibilities of being in iron 2 plus, 3 plus, 3 plus, 4 plus, and so if you have these kind of oxides on top of the surface. So, what can happen? So, if you have electron and hole generation, even with less energy, you can create these levels where electron in the conduction band can go to the iron 3 plus, and iron 3 plus will get converted to iron 2 plus. So, you start with Fe3 situation. So, iron is 3 plus, but iron 3 plus when it gains an electron becomes iron 2 plus, and if you have a electron which is coming, you can do this reduction. Now, if you have iron 3 plus here, so if you have a hole, iron 3 plus will get converted to iron 4 plus. So, in the presence of electron, iron 2 plus, iron 3 plus will get converted to iron 2 plus. In the presence of hole, iron 3 plus will convert to iron 4 plus. So, both are possible because of the variable oxidation state of iron, and the dopant also creates addition levels. So, these levels are created additional levels. So, although TiO2 has this band gap, but the actual band gap will be due to the smaller the intermediate levels which are introduced by the metal oxide dopant, and then this gap is lower in energy than this gap, and if this falls in the visible light region, then it will become a visible light photocatalyst. So, this kind of band gap engineering then creates the dopants create additional levels and lowers band gap from the ultraviolet to the visible region, and hence this catalyst becomes active in the visible region. So, here the important thing is you have chosen a metal oxide with variable oxidation states. Now, the dopant also acts as electron hole trapping center, because here you can see this acts as an electron trap, because it is removing electrons from here, and this way you can, if you can choose some other material, it can act as a hole trap, right. So, you can have dopants which not only lowers the band gap from UV to visible, but they are also acting as electron hole trapping center. Finally, they also can be used as carrier agents to facilitate migration of electrons and holes to the reaction sites. So, wherever reaction is occurring, because of the presence of these metal oxides on the surface, they act as good carrier agents, because they help in the migration of the photo generated electron and holes. So, two things here are important as usual: charge transfer events, how the electron and hole are created, and then migration of these charges to the surface. Both these effects enhance the efficiency of the photocatalyst. Now, this is a case where it is photosensitization using visible light. So, how you are going to use visible light? Using a dye which acts as a photosensitizer. So, in the previous case you brought down the band gap by adding metal oxide as dopants, and then visible light became useful to make it act as a photocatalyst. So, TiO2 with the iron oxide dopant became a photocatalyst in the UV, but here you are not using a metal oxide, you are using a dye which is an organic compound. So, you see this large molecule with the aromatic rings and some pendant substituents. You can see that this dye, which is sulforhodamine B, this particular dye can be used to sensitize TiO2, because the energy levels of this sulforhodamine dye is in the region of the visible light. So, using the energy levels of the dye of the sulforhodamine B, you can excite the sulforhodamine B using visible light, such that the electron goes to a excited state, and this SRB excited is the excited molecule, and then the electron in this state can be transferred to the conduction band of TiO2. So, the visible light is basically taken up by the dye, the sulforhodamine B dye here, and electron gets excited, and in the excited state the sulforhodamine B then transfers an electron to the conduction band with which it has an interface. So, the dye is doped onto the TiO2. So, this electron is transferred to the conduction band, and then that electron can be further used for reduction. So, it is then acting as a catalyst, because it will do this reduction reaction, and if some molecule is there which can pick up an electron, then that will get reduced. So, what happens to this molecule after it loses this electron? The sulforhodamine B excited molecule, after it loses an electron, it becomes a radical cation. So, after removal of the electron, the electron goes to the titanium dioxide, then the sulforhodamine B becomes a radical cation, and then it reacts with oxygen further, and then that forms another radical cation, and which finally decomposes to form a smaller molecule. So, this organic structure gets decomposed. So, that is also a catalytic reaction. That means, you are trying to remove an organic dye, you are broken the organic dye by exciting the organic dye with visible light, and this photo degradation of the organic dye through a radical cation in the presence of oxygen can be seen, and the final degradation products of this chromophore. Chromophore is something which can give out light. So, because it fluoresces, sulforhodamine B is has a property of fluorescing, and so it is called a chromophore and is a organic compound. So, here we are more interested in seeing that how titania was photosensitized using visible light, and the dye breaks down and gives rise to some products plus maybe some ions like sulphate ion, ammonium ion, and gases like carbon dioxide and water vapor. And this electron of titania is also used for reduction. So, this is a case of how organic dyes having a particular difference in the energy levels in the ground state and excited state can be used in conjunction with TiO2 to act as visible light photocatalysts. So, important thing, very important thing is that this energy gap should be such that it can be, this molecule can be excited with visible radiation, and then only you can get this SRB star, which means the excited sulforhodamine B. This is the ground state of sulforhodamine B, this is the excited state of sulforhodamine B, and from the excited state electron transferred to conduction band of TiO2, and then it becomes radical cation and further undergoes degradation in the presence of oxygen, and this electron can be used for reduction of some other species. So, this was another case. So, we studied cases of metal doped titania, core shell titania decorated with metals, then a core shell titania with an interfacial layer in between, how it can become efficient UV photocatalyst. Then we added metal oxides where the metal has variable oxidation states, and how that can enable titania to be a visible light photocatalyst. And then this was a dye sensitization. So, the dye, an organic dye is used which has particular energy levels which can accept visible light, and hence it is a visible light photocatalysis that can be observed using the sulforhodamine B as an example, and the electrons in TiO2 can further reduce other agents. Now, this another property, the previous one we photosensitized using visible light. Now, let us look at another problem where we can do photocatalysis using UV light and with the dye, but this is another mechanism. So, under UV light, under UV light the energy will be absorbed now with TiO2. In the presence of visible light, TiO2 cannot accept the radiation because of the lower energy, but the sulforhodamine B accepts the radiation. In this case, the UV region, the higher energy light is being accepted by the TiO2 nanoparticles, because it matches the energy. So, 3.2 electron volts is in the ultraviolet, and so you will have electron generated in the conduction band and holes in the valence band, and so this electron can then reduce oxygen, and this hole can then act on the dye. So, here we are looking at addition of a hole on the dye to create again a radical cation of sulforhodamine B. This again is simple from here what we studied in the previous slide, that the radical cation then acts with oxygen to give you another radical cation, and that breaks down to give you small molecules like diethylamine, NN diethyl acetamide, etc., and then in the presence of holes or hydroxyl radicals, it gets converted to this simple molecules or ions. So, in the previous case, the radical cation of sulforhodamine B is formed by the removal of electrons from the excited state of sulforhodamine B, and you get the radical cation. The same radical cation in this case you obtain not by removal of electrons, but by addition of hole. And so, two different processes, one acting in the presence of UV light and one acting in the presence of ultraviolet light, in the presence of sulforhodamine as a dye or an organic reagent, how the same product of the dye occurs can be understood, because in this, although the mechanism is different, in this case the sulforhodamine B degrades through the addition of a hole, and in the previous case the sulforhodamine degrades by removal of electron and then goes oxidation and then degradation. So, two different things using similar materials TiO2 and sulforhodamine B as the organic dye, but the different mechanism of the degradation of the dye is due to the different energy that you are supplying. In one case you are supplying visible light, in the other case you are supplying ultraviolet light, and hence the mechanism changes and the degradation happens due to electron in one case, that loss of electrons in one case, whereas in the other case it is addition of holes, but both cases lead to the radical cation of sulforhodamine B and then further reduction, further degradation in the presence of oxygen. Now, let us look at few other case studies where we will see what is the role of network of corner shade octahedral units of metal cations. So, we will see when you use metal oxides other than TiO2, these are not TiO2 or these are other oxides, why they are photocatalysts in certain cases, especially when you have corner shade octahedra, it shows high photocatalytic efficiency. Then what is the role of the dipole moment and distortion in symmetry, how it affects the photocatalytic properties. Then effect of the electronic band structure, that is the overlap of the orbitals of the metal oxides. If there is good overlap, the bands will become broad and things will be different, and so effect of overlapping of orbitals leading to changes in the electronic band structure. Then what happens when you have a mixed configuration of metal oxides. So, we will look at some of the cases which have these different properties. So, in this particular case, this is the basically you are looking at how the overlap of the metal particle, metal and the oxygen, their orbitals overlap, and if it is good overlap or bad overlap, what happens to the photocatalytic properties. So, these are not TiO2, now we are discussing other oxides, say this is a tantalum based oxide and it can be having a third element also. So, there is some rarer tantalate or barium dependent tantalum oxide, etc. So, this is rarer tantalate LaTaO4, in which case you have an orbital of tantalum 5D or band of tantalum 5D, all the orbitals of 5D overlap to form a band of tantalum 5D, which looks like this, and this is the energy scale, and this is an oxide. So, you will have oxygen levels, and the oxygen levels are here much below the tantalum 5D levels, which means this band has been formed from the 5D orbitals of tantalum, and this band has been formed from the 2p orbitals of oxygen. Now, when you have lanthanum also, lanthanum appears to have very sharp band or narrow band, this is called a narrow band, because the width of the band is very broad here in tantalum, where compared to that this is very narrow, is almost like a discrete energy orbital. Okay. But now, the energy of the lanthanum 4f orbital, which is a very narrow band, is lying somewhere in between within the energy levels possible for tantalum 5d band. When such a thing happens that the orbital energies are similar, then there is good overlap of bands. So, there is excellent overlap of the lanthanum 4f and tantalum 5d bands, and good overlap of these bands increases the activity of the catalyst, and that is overlap of that is the case shown here, where the highest activity is reported because it has excellent overlap of the lanthanum and tantalum orbitals and bands. Now, here you see that this narrow band has shifted down. This is the case of cerium, and so it will have moderate efficiency, whereas in this case where the praseodymium compound, the narrow band of corresponding to the praseodymium 4f orbitals is much lower and has no overlap between the tantalum 5d orbitals which are contained in this band with the praseodymium 4f orbitals. So, there is hardly any overlap, and if there is no overlap, then this acts as an electron trap. So, once electron comes, it stays here, and so it can act as a electron trap, especially in the 4f orbitals of praseodymium, since it is a narrow band. The more wider the band, there is more delocalization. The more narrower the band, then it is complete localization and very little electronic movement. So, it acts like a electron trap. So, from the band structure, these kind of diagrams are called band structure diagrams and give you a lot of idea about the possibility of the movement of electrons, the conductivity of electrons through electrons, and the band gaps and difference in what will be the optical band gap. All this you can understand by looking at the detailed band structure for these oxides. So, one thing is clear, that better the overlap of the orbitals, higher is the activity, and poorer is the overlap of our orbitals or bands, then the activity will be very low and the electron will be trapped, and the electron will not be able to reduce anything because it is trapped there. Now, it is also possible that you can have a high activity without even a co-catalyst. A co-catalyst sometimes is added, which helps in reducing the band gap or helps in effective electron transfer or hole transfer. Now, zirconia has a band gap of 5 electron volts, and it is a unique photocatalyst that shows a very high activity, and the reason of this is it has a high negative flat band potential. So, if your flat band potential is very high, then your it should be negative. The high negative flat band potential will lead to very good photocatalysis. So, this is an example, zirconia is an example of that. Another very important thing is corner sharing octahedral unit. So, many structures are known where the metal oxygen bonds are within an octahedra, and these octahedra are corner shared or edge shared or face shared. Now, the most important and a large number of compounds are known where there are corner shared octahedral units of the metal cations. So, if it is a tantalate, you have TaO6 octahedra. It is a niobate, you have a niobium O6 octahedra, and these niobium O6 octahedra or tantalum O6 octahedra are corner shared. Okay. Now, if they are corner shared, then it appears that the activity is very high, because this corner shared octahedra as shown here will help in migration of electrons and holes, and this will be this has been shown to be very good photocatalyst for water splitting reaction, and the reason is that tantalum oxide is highly connected corner shared octahedral units, whereas the rare earth, the lanthanum, also has an octahedra, but it is not connected to the tantalum octahedra. In such cases, the photocatalysis is very high. There is another example where you have two types of octahedra, tantalum oxide and another rare earth oxide, but when there are two types of octahedra and they get interconnected, then the activity for the photocatalysis decreases. So, what it means is you need one this tantalum oxide or niobium oxide, whichever is going to act as the main site for photocatalysis, should have this corner connectivity of octahedra, and it should not be interfered by some other octahedra, say of a rare earth. So, if it is unhindered, then the activity is very high. If it is hindered by other octahedra, then it becomes inactive. So, this is very important, the role of corner shared octahedral units and the presence of linear chains of these octahedra is very important. If you have distortion in octahedra and if you have dipole moment, then what is the effect on the water splitting or photocatalysis activity? Now, the activity for D10 metal oxides is strongly dependent on the distortion, on their structure, and you can see that whenever you have a distortion, then you will have local internal fields which will contribute to electron hole separation on photo excitation. Now, if you have distorted gallium oxide like this, which have a net dipole moment, they were found to be photocatalytic activity. So, dipole moment will be generated as a cause of distortion. So, whenever you have a distortion, you have high dipole moment. This is 0 dipole moment, very low activity. This is high dipole moment and this is high activity. So, distortion high, dipole moment high, and so it will lead to higher activity. So, there is another case how you can increase the activity by better overlap of metal oxygen orbitals, and you can increase the bandwidth by having good hybridization or overlap of metal oxygen orbitals, and that will also give you increased mobility of the photogenerated electrons in the conduction band and lead to high photocatalytic activity. So, these are some of the examples of oxide photocatalysis based on D0 metal ions. So, you can see titanium anatase and very good photocatalyst you can see of lanthanum doped sodium tantalate, where you have TaO6 octahedra, and these are linear and shows very high efficiency. So, with these examples I will come to the conclusion of this lecture today, and then we will have our continuation of these lectures in our next class. Thank you very much.